next we have our introductory talk of paper synthesis of single length cycle to attractor CA using NSRT diagram. The authors are Suvadip, Hazra and Mamata Dalui from the NIT Durgapur, and this paper is going to be presented by Mr. Suvadip Hazra.
Yes, ma'am. Am I audible?
Yes.
Okay. Good afternoon, all. I am Suvadip Hazra. Today, I am going to present my paper on a topic: synthesis of single-length cycle to attractor CA using NSRT diagram. This is the outline of today's presentation. At first, I will introduce about my work. Then I will discuss the motivation behind this task. Then I will discuss some terminologies of cellular automata. Next, I will discuss one tools, that is graph-based tools, that is next state RMT transition diagram, which we have used in our work. And in NSRT diagram, we will first discuss how we can identify the NSR, and from that how we can construct the NSRTD. And then I will discuss our proposed methodology, and at last I will conclude my presentation. So the introduction of cellular automata is an important milestone in the history of computing, and it is a discrete model that is increasingly being used in scientific studies and simulation. The three-neighbourhood two-state CA is a simple and elegant structure, and in the recent year, it is proved to be a powerful modeling tool. And however, the characterization of such machine is still area is research.
Wait a minute, Shubhadeep,
Yes,
your slides are not being changed. Huh? So
Okay, sir.
maybe go to the presentation mode and then.
Now it is visible, sir?
Yeah, now it's okay. Yeah.
Okay. So three-neighbourhood two-state CA has a simple, elegant structure, and in the recent year, it is proven to be a powerful tools. And however, the characterization of such machine is a still area of research. And while the characterization of the state space of three-neighbourhood CA, it is found that researchers have found that in the course of dynamic development, the nearby state asymptotically approach toward the collection of state, which is known as attractor. And the CA that has only fixed point attractor is a prime interest of devising schemes for different applications like cryptography and authentication, pattern classification, or wireless sensor network, finding the faulty nodes in wireless sensor network. So in this work, we have utilized a graph-based tools, that is NSRTD, that enables us to characterize the rules for synthesis of single-length cycle to attractor CA. And the NSRTD is also capable to explore the existence of multiple cycle as well as fixed point attractor. So this is the motivation of our work. So Chaudhary et al. Proposed a technique to identify the attractor for a linear and additive CA. Next, a graph-based scheme is proposed to identify the attractor. Is proposed by McLean et al. And they employ the De Bruijn diagram, and they have proposed a quadratic time algorithm to determine whether a linear CA is reversible or not. And another graph-based scheme is proposed, that is rule vector graph. It is proposed to identify the irreversibility of a CA. And similar kind of CAs, work is proposed for the periodic boundary CA by Maiti et al. But what we identify that the characterization of CA for fixed point, it is not well explored. Means the algorithm, there is no algorithm that can identify the characterization of CA with fixed point in linear time. So we have worked on this. So this is the basic some basics of cellular automata. Cellular automata is nothing but a finite state machine, and each cell updated in each clock cycle. This is a diagram of a two-state, three-neighbourhood CA. State can be either 0 or 1, and the next state is present dependent on the left neighborhood, right neighborhood, and the cell itself. In a two-state, three-neighborhood CA, there can be total 256 rule. Among all the 256 rule, we have listed only 3 rules here. The combination of present state is known as the RMT. So 110 is the fourth RMT, and the next state of fourth RMT is 0 for rule 15. If all the cell is employed with the same rule, it is known as uniform CA. Otherwise, it is known as hybrid CA. So what is next is attractor. In cellular automata, a set of state is forming a cycle. It is known as attractor. In the diagram, a uniform CA which employ rule 16, 0 is forming a cycle, so it is a attractor. Next is SLCA. SLCA is CA having at least one, must be at least one fixed point attractor and multi-length attractor. Next is SSCA. SSCA is single length attractors. In SSCA, there will be only one fixed point attractor. There will be only one connected component, and there will be one fixed point attractor. A uniform CA of rule 16 is a SSCA. It is because it is forming a one single length attractor. Next is TSCA. A SLCA that is forming two connected components and each having one fixed point attractor. A uniform CA of rule 38 is an example of TSA, as it is forming two connected components and each having one fixed point attractor. Next is we have utilized the next state RMT transition diagram to synthesize the TSA. This is the basic terminology of next state RMT transition diagram. First one is NCR. NCR is next cell RMT. Suppose TIT represents the RMT of ith cell, and based on which the ith cell changes state at time instant t. Then Ti plus 1t represent the NCR of TIT, and this relation must be hold. So NCR of Ti plus t will be 2TIT mode 8 and 2TIT plus 1 mode 8. So NCR of T0 will be 2 into 0, that is T0 mode 8, and another will be 2t plus 1, that is T1. Similarly, for NCR of 2 will be 4 and 5. Next is NSR. NSR is next state RMT. If TIT represent the ith cell RMT based on which the ith cell changes state, then TIT plus 1 represent the next state RMT for the cell I. And NSR is next state RMT sequence. A sequence of NSR based on which ith cell changes state is known as next state RMT sequence. For a ith cell of rule Ri, the all possible NSR sequence can be represented by a directed graph. It is known as NSRS graph. Next is the NCR, NSR, NSRS, and NSRSG is enabled to construct a set of directed graph, which is known as NSRT diagram. Next is compatibility class of NSRSs. Two NSRSs, that is, I suppose I cell NSRS is NSRS I, and I plus 1 cell NSRS is NSRS I plus 1. They are called, they will be compatible only if this condition is satisfied. That is, jth NSR of NSRS I plus 1 is NCR of jth NSR of NSRS I. So from the first step of constructing NSRS graph is we first identify the NSR. So for identifying the NSR, suppose X, Y, Z is the RMT of rule I, and based on which the I cell changes state. L represent the I plus I minus 1th state, and R represent the I plus 1th state. Then NSR, the next state RMT will be DL, D, and DR. Then the following condition will be always true. For a null boundary CA, the leftmost cell will be always set to 0. That's why the value of X will be always set to 0, and value of L will be always 0. And the rightmost cell may be either 0 and 1. Similarly, for the second cell, intermediate cell, second last cell, and the last cell, this condition will be always true. So this is one example of how to identify the NSR. Suppose we want to identify the NSR for rule 7. We want to identify the NSR for the first cell. So for the first cell, the leftmost cell will be always set to 0, and YZ will be 0, 0, and R may be either 0 and 1. So that is, we want to identify the NSR for RMT 0. So for the 0, 0, 0, the next state for 0, 0, 0 is 1. So this value will be 1, and 0, 0, 0, the next state for 0, 0, 0 is 1, and another, it may be either 0, 1, 1. So next state for 0, 0, 1 is also 1. So NSR of 0 will be 3. Similarly, we can identify the NSR for second cell, intermediate cell, second last cell, and last cell also. This is the all NSR for the all the RMT for the first cell, second cell, intermediate cell, second last cell, and last cell. From this NSR, we can construct the NSRSG. How we can construct the NSRSG? So there is T3 is the NSR of RMT0. So there will be connected edge from T0 to T3. So you can see that from T0 to T3, there is a connected edge. Similarly, the NSR of 3 is 0. So that's why there is a connected edge from 3 to 0. Similarly, NSR of T2 is T2. So there is a self-proof in 2. By combining all these, we can get the first cell NSRSG. Similarly, we can identify the second cell NSRSG, so last cell, intermediate cell, and second last cell also. And from the NSRSG, we can construct the NSRT diagram. So by finding out the compatibility class as 2, and there is a self-proof in 2, and there is in self-proof in 5. In the first cell, we can identify that there is a self-proof in 2 in the first cell, and in the second cell there is a self-proof in 5. So as 2 and 5 are compatible because 5 is NCR of 2. So there is a connected edge from 2 to 5. In this way, 2 also NCR of 5. So different graph can be constructed, and all the graph G1 represent a fixed point attractor, and graph G2 and G3 represent a multi-length attractor. So in this work, we have synthesized the non-uniform TACA using the NSRT diagram. So what we identify that depending on the specific application, the TACA may be required. And in this work, we have proposed a methodology to synthesis the TACA with any number of fixed point. And in this work, we have proposed two algorithms which can synthesize the TACA. This is the first algorithm. This is basically identify the self-loop and multi-length cycle in each NSRSG. So what we have to identify first? First, we have to identify the NSR in first cell, second cell, intermediate cell, second last, and last cell. And from the NSR, we will construct the NSRSG for the first, second, intermediate, second last cell, and last cell. And from the NSRSG, we will construct loop. That is, loop will contain the self loop as well as multi-length loop for each cell, that is first, second, intermediate cell, and second last and last cell. And the next algorithm, what we'll do, it basically do the synthesis of the TACA. For the synthesis of TACA, what it will do, we can choose the first rule randomly from all the TACA rule. For the second identification of the second rule, what we have to compute, we have to compute the compatibility class between LP1 of rule 1 and LP2 of R2. That is compatibility class between 1, 2, and choose R2 such that there will be exactly two pair of self loop NSRS, and there should not be any pair of multi-length NSRS. If we identify this type, if this condition is true, we can identify, choose any rule. Similarly, for the second cell, third cell, we have to compute the compatibility class between LP2 and LPI. LPI is nothing but the loop in intermediate cell. And we can choose any rule that if the in the compatibility class there is exactly two self loop and there should not be any multi-length cycle in the NSRSG. Similarly, we can identify the second last cell also, and for the last cell. This is the details algorithm. This is the one example of synthesizing of TACA of 5 length. As we can see that we can choose any rule, any TACA rule among the all 15 TACA rule, we can randomly choose any or one of them. Suppose we have identified 180 as a first cell rule. Next, we have to compute the compatibility class between 180 and second cell rule. As we can see that in the first cell, there is self loop in R0 and R1. In case of second cell, there is a self loop in R0 and R1 also. So R0, R1 is compatible. Similarly, R0 and R0 also compatible. So there is exactly two member in the compatibility class. So rule 52 can be chosen because in the compatibility class there will be exactly two members. Similarly, for the third cell, we can choose 166 because in the compatibility class there will be exactly two members. Similarly, 244 and 52 can be chosen for the fourth and fifth cell respectively. If you construct the NSRT diagram, we can identify there will be exactly two paths, and each path will represent two attractor. So it is the resulting CA is a TACA. So in this work, we have identified the synthesis mechanism of TACA, and we have utilized NSRT diagram to find the synthesis of TACA. And the worst case complexity of this algorithm is for a end length, for synthesizing a end length TACA, the worst case complexity will be 15 to the power n. But our aim is to synthesize TACA in linear time. This is the sum of the reference which I have used. Thank you.
Thank you, Suvadip. Thank you for the sharing this knowledge. And from the audience, anyone has any question? Okay, that I have one question.
I have one question. Can
Yes.
I?
Yes.
Okay, there is.
Okay. Like suppose we select an n cells here, and in between from 0 to kth rule you have already selected
0
to kth position. That is k less than n. And next you have to select the k plus 1th rule, na? So all the time you get the compatibility rule. That means you have
yes,
all the time. Every time.
Every time we have to find out the compatibility class. If in the compatibility class, if there is exactly 2 members, then only we can select the next rule.
That means this situation can't arise at one time, that when you can't get a 2 attractors here. That's no. That means every time you can get a next rule which can produce the 2 attractors here.
Yes. If there is exactly 2 members in the compatibility class, so there will be 2 graph NSRT graph.
Okay. Then all the rules, like from 0 to 255, all the rules.
For this one I have only considered only the TACA rule. I haven't considered total 256 rule, but the algorithm will be same for the total if we consider the 256 rule also. But for this one we have only considered the 15th TACA rule.
15th, na? So that means out of 256 you consider only 15th.
Yes. But the algorithm will be same if you consider the total 256 rules also.
But I think when you take all the 256 rules, at that time at one time you can't get a k plus 1 rules which will be not compatible with the 2 attractors here. That's my suggestion, I think, because you have only take the 15 rules out of 256 rules. And you tell that the algorithm can deal with all the 256 rules.
Yes.
Is it possible that algorithm can deal with 256 rules?
Yes, it can possible, but the complexity will be higher. If you consider 256 rule, then the complexity will be higher, but the procedure will be same.
Procedure will be same, but complexity will be maybe
yes.
It's exponential, or either it's
linear.
It
is exponential.
Okay, that's my question. Thank you.
Okay.
Thank you. Okay. Thank you. So nice talk.
Thank you.
Okay, from my side, one query is there.
Yes,
that, can you share this? What are the 15 rules among this 256 rules?
Okay, 1 minute.
Najma, your question, you please repeat the question, Najma.
What are the 15 rules among the 256 rules for which this algorithm will?
Okay, 1 minute. Is it visible?
Yeah, you're audible as well as visible.
Okay. It is not like that. If we consider only 15 rule, these 15 TACA rule, the algorithm will work. The algorithm will work if you consider total 256 rule also, but on that time the complexity will be higher.
Right now, I think in this paper you are proposing an algorithm that will take the linear time.
No. This is taking exponential time, but our main aim is to design a synthesis mechanism so that we can synthesize the TACA rule in linear time.
Okay.
Yes.
And another query is that what is the difference between the reachability tree and NSRTD diagram? That
I think in the reachability tree, you cannot find the multi-lane cycle, right? But in the NSRTD, you can find the fixed point attractor as well as multi-lane attractor also.
using reachability tree we can, but it will in the worst case it will be exponential.
Okay, okay,
And also in that TACA also we can find with the linear time.
okay.
I have just one query, Suvadip. These 15 rules have some properties, common properties.
Common property in the sense, in which sense you are?
No. You select that 15 rules, na?
Yes.
So,
These all these rules are TACA rules.
TACA rules, that's okay, but what property they have? That's why you select it.
No, because I am synthesizing TACA, that's why I am considering only the TACA rules.
Okay. Thank you.
No, maybe Shumit is asking, maybe Shumit, your question is, what are the properties of rules which you have chosen for TSC?
Yeah. That's my question, but yeah. Okay.
Shumit, any calculation you have done, or you have done it through experiment?
I have done it through experience. Sir.
Okay. So is it a future scope to theoretically analyze these rules?
And yes, we can design an algorithm so that the synthesis can be done in linear time.
Okay. Thank you.
Which we have already done this part. Okay, sir.
And also check your algorithm that it's work for the all the rules, 256 rules.
Okay.
Check it, please.
Okay. Thank you.
Thank you, Suvadip, for your nice presentation.
Thank you.
With this paper, we'll this journey of this ASCAT 2020 will completed, and